All right, so welcome to the lecture series on high performance deep learning. So a little bit about me. My name is Eric Marcus. I'm a postdoctoral researcher at the University of Amsterdam and the Netherlands Cancer Institute. And in this course, we want to talk about how to effectively use large amounts of compute to speed up all your research and other applications. And so in particular, let us just dive into it. Let me open up the slides here. All right. Yeah. Okay. So cool. And in this particular module, I want to talk about the multi-GPU training. So let me give you a bit of an overview as to what I want to talk about. So I basically divided in three regions. We were going to start off by doing a more theoretical approach, where we're going to go through a couple of things. So we're going to talk very shortly about why GPUs are interesting in the first place, why would we use multiple GPUs, then we're going to dive a little bit deeper and go into what kind of GPU operations can we actually use. And then we're going to go to practice level 1, where we're going to talk about PyTorch and what kind of frameworks are implemented in there. So there's a couple. And then at the end, we're going to go to the practice plus, where we're going to talk about PyTorch Lightning, and how incredibly easy it is for you to implement all of these kind of multi-GPU things when you're making stuff in PyTorch Lightning. And I'll also tell you a little bit about how you could possibly track performance of your experiments. So let me very shortly go about why do we use GPU. So some of you, of course, might already know. So when I'm talking about the AI stuff, so a lot of what we do is, of course, neural networks, and the computations that are associated with neural networks, they're called embarrassingly parallel. The name kind of gives it away. So all the calculations that you're doing, which are like matrix multiplications, they can be executed in parallel, and they're practically completely independent. And those are exactly the kind of computations where the architecture of a GPU, so a graphical processing unit, or the original name, they excel at those kind of computations. So if you look at the picture, you can see the idea that I'm trying to convey. So the GPU architecture consists out of a load of these cores, or the green squares in the image, and all of them will, in a way of speaking, do then those independent computations at the same time. Whereas the CPU, the central processing unit on the left, has way fewer cores, but is way better at doing more complicated things. So that is, in a nutshell, why we would use GPUs in the first place. So now, of course, you may be wondering, okay, so what about multiple GPUs? Whenever would I need this? So I just thought I can give you a couple of examples. So the first one I want to discuss is the OpenAI's CLIP model, and this is a very large model that is trained on a combination of text and images, with the eventual goal of like making a caption for an image. So the thing is, the data set they use for this is absolutely enormous, and it consists out of 400 million pairs. So we can try to wonder what it would take to do it on our little household GPU. And you can do a little hand wavy calculation, and to show like how long would it take to go through these 400 million data points, and it's approximately 30 years. And I don't think a lot of people are very interested in waiting for such a long time. So what they did instead is just use 600 GPUs and do it in 18 days, a couple of weeks. And that's just one of the reasons why you would do it, because nobody is going to sit around and wait for 30 years for the calculation to complete, of course. Yeah. So on the right you still see the image of what the pre-training looks like for OpenAI clip. So another example is more one of my own. So together with a PhD student, we set out to create artificial images of lung nodules. So nodules, they can be a lot of things, but they could be tumors, for example. And so the idea of this is where you can extend the existing data by just creating fake images alongside it. So I included some images here where you can see what's happening. So on the left images, that's the input for the model, and on the right is the output. Now, of course, you might need a bit of a trained eye to judge how well it is doing, but I suspect that if you stare at them for a bit, you can at least see that there is some kind of nodule-shaped thing, and in fact, they're doing really quite well. But also for these models, so these generated models, you need large amounts of data, and the models themselves can also be quite big. So you really want to parallelize this out, because otherwise you're going to end up waiting not 30 years, but a pretty long time. So that's another example. So there could also be another reason where you have models that are so large that they cannot even fit in a normal GPU. Now, this is pretty rare, and you really need to do extravagant things before it happens, but I included one example which you have probably heard of, which is GPT-3, which is a large language model that also OpenAI made. And so the largest one is, well, I think in this table at least it's 175 billion parameters, and well, there is no way you're going to fit that in your average GPU. So you have to be a bit smart about it and think, how can I solve those problems? But for now, so let me reiterate. So the main reason why we are interested in it is to distribute data over multiple GPUs. So the model's too large. There's also very fun things to do with that, but it will not be our main focus for the rest. So now let me move on to a next level here, which is the back end. So there's basically a question of how do we control the GPUs, right? So who is telling the GPUs what to do? Now, and of course, with any kind of programming scenario, there will be various layers of abstraction. So we're mostly going to be working in PyTorch Lightning, also in this tutorial, or actually also some PyTorch. And then there will be increasing layers of abstraction. So PyTorch will communicate via some backend, and those backends are of course made again in C++ and CUDA. So CUDA, for those of you who are not familiar, is like an extension. I don't know if I'm allowed to say an extension of C++ to also work with the GPUs, well made by NVIDIA. But that's not going to be our main focus. That's a bit too low level for this course. And so we're going to mostly be focusing on Lightning, PyTorch, and a bit the back-end operations and how they control what the GPUs can do. So let's have a little look. So there's an enormous table here. Do not worry, you do not have to know this by heart in any way whatsoever. But it's just to give you an overview as to what is happening. So we're discussing PyTorch here, and PyTorch has 3 backends to do multi-processing, right? So it's not only multi-GPU, but there's also multi-CPU. But of course, we are focusing on GPUs. And there's a couple of them, yeah. So I'm just going to say the most practical thing to say is that in general, this nickel one, this is the way you pronounce it, is the rightmost column in the table. That's generally the most fast one and versatile one. You can also see in the table that it supports almost every operation that we can think of. Now, of course, currently you have no idea what those terms mean, but we will, by the end of this course, you will be quite familiar what it all means. And so when you use Nickel and you configure it appropriately, there will be near linear scaling, for multiple GPUs, which is of course amazing. I will include in the video description a link to a paper that discusses this in more detail for those of you that are interested. Okay, so those are the backends. Now we want to know what do I mean by that? What are all these operations? Now let me check. All right, yeah. So let me go through these operations. Yeah. So we're going to start off with a basic dictionary here, which is going to go through some terms that are very common in the multi-processing, multi-GPU world. So the first one that we're going to discuss is what is going to be the groups, the worlds, and the ranks in the basic dictionary. Then we're going to go to the actual operations, point-to-point, and collective communication. So there's just different names for different operations. And we'll just go through them with some example. I won't go through all the operations, but I will go through enough such that you can figure out yourself what the rest are. And in the tutorial, we'll look at some more in some depth. Cool. So dictionary. Let me mention some words. So the first word is node. So probably you have heard this one before. It's just a system in your computing cluster. So for the UVA students, so Lisa is a computing cluster, and there's lots of nodes on there on which you can ask for GPUs and whatnot. And then we can think about what does rank mean. So rank, there's a couple of meanings. So let me start out with this one, which is the global / node rank. And that's like a unique identifier for the node in your experiment, right? So there may be multiple nodes in the end of your experiment, and you want to make sure, okay, that one is that one, and then everything is clear. But of course, for each node, there may be multiple GPUs. Right, so what we do is we have a local rank, which for each of these nodes tells you, okay, this process is identified by this number, the rank. Now, and usually, as we will see later on, each GPU has its own process, meaning that the ranks are kind of synonymous with GPUs. Yeah, so that's the local rank. And then there is one last thing, which is called the world. So the world is like the actual world, consisting out of all of your processes in the experiment you're doing, and they all live together, in the sense that they can communicate with one another. And then the world size is the size of the length of all the processes, right? So there, if you have like one node with 3 GPUs, then the world size will be 3. And we will see some of these terms in more detail in the tutorial as well. Cool. So that's the basic dictionary. Now I want to move on to point-to-point communication. So this is the most basic operation that we can do between multi-GPUs. So any point-to-point communication, as the name may already suggest, just consists out of sending something and receiving something. So those are also the two operations, right? And they can be used in any kind of pattern or form. So here I show you a little pictorial example of it. So here I have, let's say one node with 4 ranks. So if each GPU has its own process, you can see this as like 4 GPUs. And then, here rank 0 sends something out to rank 3. So rank 0 is using some kind of send operation, and rank 3 is receiving it. Yeah, couldn't be easier if we if we think of it. So for each of the operations, I want to give you a bit of an intuition why and when would we use this. So for this one, the point-to-point is of course, you do this if you really want to have very fine-grained control. So if you really want to do something where you want to squeeze the last bit out of it. So let me give you some real-life research examples where people really had to go down to the point-to-point communication and use this. So here you see two papers, one by Facebook and one by Baidu, and they both really, because they're very high performance models, they kind of build it from the ground up and use these operations in excruciating detail. So you're free to look up these papers and investigate for yourself, of course. But okay, so point to point, just sending and receiving. There isn't much more to say about it. So let me go on to what is called collective operations. So they involve, basically all of the ranks. That is the idea of collective operations. But there is already something that we have to be careful about, because suppose that we do a collective operation, but one of the ranks is not completing it, then the whole world will be forever waiting for that rank to complete the operation, resulting in a so-called deadlock, which is obviously something we want to prevent from happening. So keep that in mind. So anyway, let us continue to the first one, which is called scatter. And so this operation, as the name may suggest, it scatters out something from one rank to all the others. So here I have made a little pictorial example where on rank 0 we have, for example, one list of a 0, 1, and a 2. And when I scatter it, it means that I distribute this list among all ranks, including also 0 in this case. So rank 0 gets 0, rank 1 gets 1, and rank 2 gets 2. Easy enough. So you might wonder, okay, so where is this used? This is, for example, used when we want to divide the batches among ranks. So we will see later on, this is kind of what happens in data parallel. And let me see, is it going? Okay, yeah, right. What happens in data parallel, and data parallel, okay, that's right. What happens in data parallel, so you got to imagine there is one side note here. Whoops. As you may have noticed back in the backend table, when we're talking about nickel, which maybe I've not mentioned, is the NVIDIA communications library. Scatter was actually not listed in there. Yeah, that is true. So this is the one operation that's actually so easy to implement on the lower level code that nickel was not necessary to speed it up. So you can actually just look it up in PyTorch. How do they do scatter? And it's a very simple operation. So that's a bit of a side note to how it is implemented. Anyway, so scatter out, for example, batches among all the GPUs. So you got to imagine, of course, in practice now, it's not that rank 0 has 0, 1, and 2 in the GPU memory and then starts to scatter it, because that would kind of defeat the purpose. So it's more the machine has 0, 1, and 2, and then each GPU gets a batch 0, 1, 2, which completely fills up the memory. That is the ideal situation we want to achieve. Okay. Next one is broadcast. So this one is used a lot. So what does broadcast mean? Broadcast means we're going to take some piece of data and we're gonna copy out that piece of data to each of the ranks. So in the image, you can see that so the data is copied from a root rank. So the root rank, that is just a name for the leader in the group in some sense, and it's copying his data, which is labeled by in, to all the ranks, where we're going to call it out. And of course, all of these outs are exactly equal to the in. So when is this used? This is used, for example, when we copy the model from a a root rank to all of the GPUs. So all the GPUs then get the model. So that is broadcast. Now, reduce is the next one I want to discuss. It's one of the last ones actually. And reduce, as the name suggests, it performs reductions across the devices and then writes it to one device. So reductions, it can be like doing a summation or an average or computing the maximum. And so in the image, for example, we have a sum reduction where all of the ranks have some kind of data, and they're the different colored ones, and then they're all summed across and then placed into the rank 2 in this case, which is the root. There's obviously nothing special about rank 2. Any of them could be the root. So that's reduce, and you can imagine when would we use this as well. We can have a certain metric that is on each rank, and we want to average out that metric and collect that on one of the GPUs and then do something with that. So let me very shortly mention another operation, which is called gather, which is actually used also quite often, but it's nothing else than just a reduce operation where the reduction operation is then a concatenate. So it takes all of these GPU data and it just places them in one big tensor and then gives it to one of the next GPUs. Okay, so let's move on to all reduce. And you can probably kind of guess what this does, but in practice it's just doing this reduce operation that we just saw, followed by a broadcast. That's basically all there is to it. So it reduces something and then broadcasts that result, copies it to all other ranks. And this one is actually very often used. For example, if we have a distributed data parallel thing, which I'll come to later, we're computing gradients in the back propagation of our algorithm, then we use an all reduce operation to average and distribute the gradients to all the ranks that are in our experiment. Okay, so that's kind of the last one I wanted to discuss here. So there are, of course, more operations. There's always more, and we will discuss some of these also in the tutorial. Okay, so now that was a bit the theory part that I wanted to go through. And the next thing I want to do is go to practice level 1, where we're going to look a bit at how PyTorch implements these parallel data things for multiple GPUs. So we're going to go through the most well-known ones, which is data parallel and distributed data parallel. And at the end, I will talk a bit about what else could possibly be done. Okay, so let's now go to the data parallel and use our knowledge from the theory part and understand what is happening with a PyTorch data parallel. So, well, before we get into it, let me give you a bit more of an introduction. So the idea of PyTorch data parallel is to, of course, use multiple GPUs. That's the idea of all of these frameworks that we're discussing. And as the name suggests, it's just going to try and parallelize the data immediately. So let me walk you through the steps on how we use our multiple GPUs in this scenario. So we're going to start off by splitting a mini batch. So there will be a mini batch of a very large size, a size exactly so large that it can be distributed over multiple GPUs and fill up their memories. And then we're going to use our scatter operation, which is one of the first ones that we discussed. And we're going to scatter it over all the ranks. So, and don't worry, after this there's a little bit of a movie that will show this in practice as well. So bear with me. And after we have scattered our our data, we're going to do a broadcast. So we're going to copy the model from the root rank to all of the GPUs. So at this stage, every GPU will have a piece of data and the model, right? Which is basically all we need, because the data is just going to go through the model. We're going to get some kind of forward going, which actually, of course, the next step. So you forward the mini batches through the models on all the GPUs, all the ranks. And then what we're going to do is a reduce operation. So, at this stage, we have gone through the models and we're going to reduce it. We're going to like average or sum all of the gradients that we obtain. And we're going to get them back to rank 0, our root nodes. And then rank 0 is going to take these gradients and is going to, perform the back propagation, it's going to do the back and optimize the model, right? So it's going to use all the gradients, back propagate them, optimize the model, and obtain thereby a new model. So, as you may guess, the next step is to repeat this whole procedure, right? Because now we have a new model, so we're going to scatter again all the batches, we're going to copy again the model, and go through the whole thing again. So here there's a little bit of a graphic that I will let you run for a couple of times, and then you can watch it back as much as you like. So here we can also see, if you go through it, that first we have the data, and we distribute the data over all the ranks, and then we copy the model, which is this purple thing, to all the ranks. We forward through the data through all the models, then perform some reduce where we get to rank 0, which performs the backward propagation, optimize the model, and we do the whole thing over again. So maybe one thing I forgot to mention is that actually the data parallel has one remark needed for it, that it is never possible to do this data parallel over multiple nodes. So with that I mean, on each node you can of course have multiple GPUs, but at some point when you want to scale up to using a lot of GPUs, if you want to use 100 GPUs, there's never going to be one node that has 100 GPUs, right? Very often you will see at most 8 GPUs per node, and on Lisa, for example, we see often 4. So there's already a big drawback here, that it can never scale up beyond one node. So that's already one thing to keep in mind. Yeah. And so what is another drawback of data parallel is, of course, the enormous amount of communication overhead. So you can already see, like, copying the model each time over and over is of course an insane overhead to have. So we're going to try and figure out if we don't have to do it. Well, surprise, we don't have to do it. So this is basically the idea of distributed data parallel, which is a second framework in PyTorch. And the immediate advantage is listed on top. So we're going to only once broadcast the model to all ranks, right? So we're just going to copy paste it everywhere, and we're going to make sure that everywhere it's initialized exactly the same. And then you can already guess it that at some point we'll probably update it, but we don't have to keep copying the model back and forth between ranks, because we can just locally update it, and that will save us a load of communication overhead, which is absolutely magnificent. So then let's go through what distributed data parallel does. So the first thing it's going to do is it's going to gather, again, some data. In this case, we're going to use some kind of distributed sampler, which, to be fair, might also be for data parallel, but let's just talk about it now. We're going to use some distributed sampler. In this scenario, suppose we have 2 GPUs, and our data consists out of a list of 0, 1, 2, and 3. Then, a distributed sampler could be picking out, indices of this, which are then assigned to each of the rank. So then GPU 0 could get 0 and 1, and GPU 1 could get 2 and 3, right? Which is then the data that they are going to be using for that particular forward. Okay, good. So that's the thing. So now we're going to remember, so we already have broadcasted our model at the start. We only do this once. We have now got some data. We have distributed the data. We have indices that, we're going to see. So each rank just sees one part of the data, and we're going to forward it through the model. Then we're going to obtain, of course, our losses and the gradients. And what we're going to do then, because each of the ranks will, of course, have different gradients because they've had different data. So we're going to have to make a way to synchronize this. And we do this with one of our all-reduce operations, which we discussed earlier, where we're going to do a reduction, for example, averaging. So we're going to average the gradient and make sure that they're broadcasted, copied to all other ranks. And in that way, after the forward and the all-reduce, now every node only has to communicate the gradients, of course, but they all have the same gradients now. So after we have done that, all of the ranks simultaneously perform this optimization step and update their local model. Right? Nothing has to be copied over and moved around. And of course, after that, we're going to repeat it, right? Because we now have our new models, and we're going to look at some new data indices that we're going to be looking at and forward it and backpropagate and synchronize and go on again. So a lot less overhead is needed. And this method, the distributed data parallel, is capable of running on multiple nodes. Because you can imagine you only have to do the broadcast once, initialize it, and then everyone only sees a part of the data, so you agree on this, and then you start synchronizing gradients even across nodes, which is great. So here is again a little graphic which does the same thing. So let me talk you through it. There are now two nodes, so there's node 0 and node 1, and group rank. If you remember the dictionary, that just tells us a unique identifier for each node. So that's all the text that's on top. And then, just to reiterate it, on top we have random seed is 12, which is just to reiterate the point that each model is initialized in the same way, which is of course very important because otherwise we really start doing weird stuff. And then what happens is that all the models are only copied once, which is I don't think even shown in the graphic. But then we get all these kind of data distributed, so everyone has their own little data point, and they're going to forward it through the model. We're going to synchronize the gradients with the all reduced, and then we're going to backward through the model and update it locally, which will all still be the same, which is very important. Okay, so let me give you a short overview of what we have seen. So due to the lack of the overhead, the communication overhead of copying models every time, etc., the distributed data parallel is generally much faster than data parallel. And also one thing I may have forgotten to mention, so the distributed data parallel, each GPU actually gets its own process. So the own process will be responsible for getting the data and doing all the procedures that we talked about. That's also a feature of this, which we may discuss in the tutorial a bit more, but maybe also not. I'm not 100% sure. And one thing, of course, is that the distributed data parallel is scalable across a node, and it scales well. So when at the start I said at some point that stuff is linearly scalable if you configure it right, it is using distributed data parallel, right? Obviously, data parallel can never do that because it stops at one node, for instance, already, and it's way slower. Okay, so that is a bit the two main frameworks that PyTorch has to offer, but of course, there is always more, because it may be that your models might be too large, which we talked a little bit about at the beginning, or distributed data parallel is not scaling as you expect. There is something slowing it down. For those cases, there is something that's called fair scale. And there's a little flowchart here, and maybe in another lecture we'll actually get back to this, where we're gonna, you can see there's loads of options to doing, like lots of it's called sharded. So for those of you who cannot wait for another lecture, you can start Googling sharded already. The nice thing about all of this is that even though it's very complicated, most of these things, some of these things have already been implemented in PyTorch Lightning with a very easy flip of a switch where you can just start using this. But let me not dive into this too much now. That would go beyond the scope of this lecture. So we're going to go to our practice plus. We're going to talk a bit about Lightning and how we're going to use multiple GPUs in Lightning, and very shortly and hand waves about how you can track your performance of your GPUs, which is very important to keep in mind, because you don't want to go ahead and take 100 GPUs on Lisa and they're all sitting around idle doing 1% of work. That would be kind of unfortunate. So multi-GPU in Lightning is incredibly easy. That's the good news. So it implements all of these backends that we just talked about. So this data parallel backend, the distributed data parallel, and also more. And it's all determined by a so-called strategy argument. So here I include 3 lines of code where we implement the PyTorch Lightning trainer. And I show you the 2 examples, right? So how do I do a data parallel and how do I do a distributed data parallel? Where with an obvious, statement, you should be using the distributed data parallel because it's way faster and better. And then you can just see that in the trainer of PyTorch Lightning, I can ask for how many nodes do I want and how many GPUs do I want. Where in the bottom example here, we would have 2 nodes where each would have 4 GPUs. So in total, it would be 8 GPUs in this experiment. And that's really it. That's how easy it is. They have really made this backend quite solid. Sometimes some stuff can go wrong, but if that happens, then thankfully Google exists. Of course, there are many things that I'm a bit skipping over here. So there's many fine-tuning things that are possible in the trainer and what you can do. And so in this code example, I show a couple of them. You have distributed data parallel, which is called with a spawn procedure or with a script procedure, which has its advantages. And there's also all kinds of checks that can be done in this distributed data parallel, where it's going to try and find unused parameters on which there is no gradient to be done, if I remember correctly. So those things, of course, they are also important, but you will run into them one way or another when you start doing this with Lightning. So as I said, it will work very easily, but at some point you will think oh, can I do better? And then usually there are some things you can do better. But the documentation of PyTorch and Lightning is usually really quite sufficient to get it going. So the conclusion is in PyTorch Lightning everything is super easy. They really made it very convenient. So next thing is tracking performance. So there's a couple of options to do so. So I think on Lisa and on a lot of clusters we usually install nvtop. Which is a command that you can ask for. You'll see something like this. So this is not run on Lisa, but on another cluster. So let me talk you through it. So on top there is a little bit like what devices are being used and done. So here we have 2 devices, both are very big graphic cards. And then it shows you some temperatures and clocks, which you may or may not find interesting. But then the interesting thing is the big graphs below it, which show you how much is the GPU doing, right? So how hard is it calculating? So the blue line, so there's 2, right? 2 graphs, so in both of them, blue and a yellow line. So the blue line shows you the activity. So ideally, you would see something like in the top graph, where the blue line is constantly at 100%, because that means that you're effectively using your GPU. In the bottom graph, we see something a bit more fluctuating, but it's still, above 75%. It's still quite reasonable. It could be better, but definitely could be a lot worse. So it's I would be very agreeable with this. And the yellow lines, they show the memory of the GPU, right? So the memory is, of course, where you plug in all your models, where you plug in all your batches, etc., etc. And so if you see that the memory usage is quite low, you can try to think about, can I increase my batch size? Because then I can speed up the training, maybe even get some better gradients or not. Yeah, so keep track of that. Anyway, moving on. So of course, not every cluster has NVTop, but you can of course also do the an NVIDIA SMI command as well. So it's basically NVTop, but then without the graphs. So you just see the numbers and the memory. That's an easy way to keep track of it as well. And that is, if you have drivers installed, I think probably NVIDIA SMI has to be there as well. So that's just a basic tip to keep track of that. And then, if you see that stuff is not working as well as you want it, and you have debugged a bit, you've thought about it a bit, but you cannot figure out what is causing this slowdown, there exist these things called profilers in Lightning, but in general they exist. And a couple are built into Lightning, so they have I think it's called a basic and a more advanced one, which just go through the operations and tell you how much time was spent there. But then there's even a more advanced one possible, which is called the PyTorch profiler. Now you will see something like this. So the first glance you probably think like, ooh, what am I looking at? I don't understand anything. But if you study the graph a little bit, you will get an idea of what is happening. So usually it's divided into what a CPU is doing, what a GPU is doing. And then you can try to figure out, what operations is the GPU waiting for, right? So you can see in the profiler, I think here, maybe in the bottom, the gray thing, like how much is it doing? Is it doing nothing? Right? So if you see very large gaps in the GPU, that just means that it's waiting and doing nothing. And then in this profiler, you can start to look at the CPU. It could be, for example, that you're doing very CPU intensive data augmentations, and that the CPU is just calculating, but cannot keep up with the GPU, and GPU is just waiting around. And in such cases, you can figure out what is the cause and then think of a solution. Right? You can move some of the augmentations to the GPU even, or something different. But this is a very good tool to investigate what is the problem and where does it lie, right? So that's one tip I would have you take with you. Okay, so I think that's actually the end of my slide. So I'm gonna stop the share. Yeah, and so thanks for joining today, and I wish you good luck at the tutorial, and prepare some questions for the Q&A session later on. I would advise.